So here's something that might keep you up at night, except tonight, we're going to let it do the opposite. We're going to let it ease you into sleep. And it starts with a question that sounds simple. How fast does light travel? You probably know the number, or at least a version of it. Something like 186,000 miles per second, or 300,000 kilometers per second. Or if you want to be precise about it, 299,792,458 meters per second. That number. That very specific, very exact number. But here's what's strange. That number isn't just fast. It isn't just a speed. It's woven into the fabric of reality in ways that are so deep, so fundamental, that once you start pulling on the thread, the whole universe starts to look different. And tonight, we're going to pull on that thread, gently, slowly, and see where it takes us. But let's not start with Einstein. Let's not start with relativity, or space-time, or any of that yet. Let's start much, much earlier, because the story of the speed of light is really the story of people trying to answer a question that seems almost childishly simple. When you light a candle, does the light from that flame reach your eyes instantly, or does it take time to get there? Think about that. You're standing across a room from a candle. You see the flame, but did the light travel to you like a ball thrown across the room? Or did it just appear in your eyes the moment the flame existed? For most of human history, really smart people were absolutely convinced it was instant. And honestly, you can't blame them. Light seems instant. You flip a switch, the room is bright. There's no delay you can perceive, no lag, no waiting. It just happens. The ancient Greeks thought about this a lot, actually. Empedocles, who lived around 490 BC, was one of the first people we know of who suggested that light actually travels, that it moves from one place to another, and that this movement takes time. He compared it to a person walking. The light leaves the sun, crosses the space between, and arrives at your eye. It's a journey. But Aristotle, who came along about a century later, disagreed. And when Aristotle disagreed with you in the ancient world, you were basically done. Aristotle argued that light wasn't a thing that moved. It was more like a state, a condition of the medium between you and the object. When the sun comes up, the air doesn't slowly fill with light from east to west. The whole sky just becomes bright. It's a change in the state of the air, he said, not something traveling through it. And in a way, you can see why that argument was persuasive. Because if light did travel, wouldn't you be able to see it moving? Wouldn't there be some perceptible delay? And so, for almost 2,000 years, that was more or less where things stood. Light was either instantaneous or so fast that the question didn't really matter. The Islamic Golden Age produced brilliant optical scientists like Ibn al-Haytham, who around the year 1000 wrote his monumental Book of Optics and essentially founded the modern science of how we see. He understood that light enters the eye rather than the eye sending out some kind of vision ray, which was a competing theory at the time, believe it or not. The idea that your eyes shoot out invisible beams that touch objects and report back. It sounds wild now, but it was taken seriously for centuries. Ibn al-Haytham dismantled that idea carefully and methodically. But even he didn't resolve the question of whether light's travel was instantaneous. He suspected it wasn't, that light had a finite speed, but he couldn't prove it. And here's the thing about the speed of light. For a very long time, it wasn't really a physics question. It was a philosophy question, because nobody could figure out how to measure it. And the reason nobody could figure out how to measure it is that it's so absurdly, incomprehensibly fast that any experiment you could design on the surface of the Earth would give you a result that looked instantaneous. The distances are too short. The speed is too great. You'd need a very long ruler, cosmically long, or a very clever trick. The first person to really try was Galileo. And I love this story because it's so beautifully simple and so perfectly doomed. Sometime around 1638, Galileo described an experiment. You take two people and you put them on hilltops about a mile apart, each holding a lantern with a shutter. Person A opens their shutter, and as soon as person B sees the flash, they open theirs. Person A times how long it takes from when they opened their shutter to when they see person B's light flash back. The round trip time. If light takes time to travel, you should be able to measure the delay. And if you do this at different distances, farther and farther apart, the delay should grow. It's a gorgeous idea. It's the right idea, in principle. The problem is that light covers a mile in about 5 millionths of a second, 5 microseconds. And the human reaction time to see a flash and open a shutter is something like 1/4 of a second, maybe 1/5 if you're really sharp. So the thing you're trying to measure is roughly 50,000 times smaller than the noise in your measurement. It's like trying to weigh a single grain of sand by putting it on a bathroom scale. The scale can't even register it. Galileo, to his credit, basically concluded that if light wasn't instantaneous, it was at least extraordinarily fast. He couldn't measure it, but he didn't rule it out. And that intellectual honesty, that willingness to say, I don't know, but here's what I tried, is one of the things that makes Galileo such a remarkable figure. So the problem sat there, unsolved, for another few decades. And then something wonderful happened, and it happened because someone was looking at something completely different. This is one of those moments in science that I just love, where the answer to a question comes from a direction nobody expected. In the 1670s, a Danish astronomer named Ole Rømer was working at the Royal Observatory in Paris. He wasn't trying to measure the speed of light. He was trying to make better tables of the orbits of Jupiter's moons, particularly Io, the innermost of the 4 big Galilean moons. Io orbits Jupiter every 42.5 hours or so, and it regularly passes behind Jupiter, disappearing into Jupiter's shadow. These eclipses were like a cosmic clock, very regular, very predictable, and astronomers wanted to use them for navigation, for synchronizing clocks across long distances, for all sorts of practical purposes. So Rømer was carefully recording the times of Io's eclipses month after month, trying to build the most accurate prediction tables he could. And he noticed something strange. The eclipses weren't perfectly regular. When Earth was moving toward Jupiter in its orbit, the eclipses seemed to come a little early. When Earth was moving away from Jupiter, they seemed to come a little late. The discrepancy was small but consistent, and it accumulated over months. By the time Earth was on the far side of its orbit from Jupiter, compared to when it was on the near side, the eclipses were running about 22 minutes late. Now, 22 minutes is the number Rømer calculated. The modern value is closer to about 16.5 minutes, so he was off, but he was in the right neighborhood, and more importantly, he had the right explanation. Here's what Rømer realized, and this is genuinely one of the great intellectual leaps in the history of science. The eclipses weren't actually irregular. Io was orbiting Jupiter like clockwork, just as expected. The variation was caused by the changing distance between Earth and Jupiter. When Earth was closer to Jupiter, The light from the eclipse had a shorter distance to travel to reach us, so we saw it sooner. When Earth was farther away, the light had to cross that extra distance, and so we saw the eclipse later. The 22-minute difference represented the extra time it took light to cross the diameter of Earth's orbit around the Sun. Think about what that means. Roemer was saying that light is not instantaneous. It travels at a finite speed, and it takes a measurable amount of time to cross the solar system. He announced this in 1676, and it was controversial. Some people accepted it, some didn't. Christian Huygens, the brilliant Dutch physicist, took Roemer's data and actually calculated a speed from it. He got something like 220,000 kilometers per second. That's about 26% too low compared to the modern value. But remember, the measurement of the diameter of Earth's orbit wasn't very precise at the time either. The important thing wasn't the exact number. The important thing was that light had a speed at all. It was finite. It was measurable. It was real. And I want you to sit with that for a moment, because it's easy to rush past it. For 2,000 years, from Aristotle to Roemer, the prevailing assumption was that light was instantaneous, infinite speed, no travel time. And then this Danish astronomer, watching a tiny moon disappear behind a giant planet, figured out that light takes time to get from there to here, that the universe has a speed limit built into it, even if nobody called it that yet. It's one of those discoveries that changes the shape of everything that comes after it, even though at the time plenty of people shrugged and went back to their telescopes. Now, Roemer's measurement was rough. He knew that. Everyone knew that. And for the next century or so, the question wasn't really whether light had a finite speed, but rather how to measure that speed more precisely. Astronomy had given the first answer, but astronomical measurements are inherently messy. You're dealing with vast distances that you can't measure directly, orbital mechanics that have their own uncertainties, and observations made through a shimmering atmosphere with imperfect instruments. What people really wanted was a way to measure the speed of light in a laboratory, on Earth, under controlled conditions. But that brought you right back to Galileo's problem. Light is so fast that any earthly distance seems like nothing to it. It took until the middle of the 19th century for someone to crack that problem, and the solution, when it came, was mechanically ingenious. In 1849, a French physicist named Hippolyte Fizeau set up an experiment in Paris that is just delightful in its cleverness. Picture this. He had a bright light source, and he focused the beam so it would travel in a straight line to a mirror about 5 miles away on a hilltop in Suresnes. The light would hit the mirror, bounce back, and return to Fizeau's apparatus. A round trip of about 10 miles. Now 10 miles at the speed of light takes roughly 54 microseconds. Still way too fast to measure with a stopwatch or a human reaction. But Fizeau didn't use a stopwatch. He used a toothed wheel, a spinning disc with 720 teeth cut into its edge, with gaps between them. He positioned this wheel so that the outgoing light beam passed through one of the gaps between the teeth. The light shot out through the gap, traveled 5 miles to the mirror, bounced back, and returned. But while the light was making that 10-mile round trip, the wheel had rotated slightly. If the wheel was spinning at just the right speed, the returning light would arrive just in time to be blocked by the next tooth. No light would get through. Speed the wheel up a little more, and the light would arrive in time to pass through the next gap. Light gets through again. By carefully adjusting the rotation speed of the wheel, and noting when the returning light was blocked versus when it passed through, Fizeau could calculate how long the round trip took, and from that, the speed of light. He got a value of about 315,000 kilometers per second. Not perfect, but remarkably close. And the beautiful thing about this experiment is that it's entirely mechanical. No electronics, no fancy sensors, just a spinning wheel, a mirror, and a beam of light. The precision came from knowing exactly how fast the wheel was spinning and exactly how far away the mirror was. Those were things you could measure with 19th century technology. But Fizeau's experiment was really just the opening act, because the very next year, in 1850, a rival physicist named Léon Foucault, the same Foucault who would later become famous for his pendulum demonstration that proved the Earth rotates, came up with an even more elegant method. And the rivalry between Fizeau and Foucault is one of those quietly intense scientific competitions that doesn't get talked about enough. They had actually worked together earlier in their careers, collaborating on experiments with light and photography, but they had a falling out. And by the late 1840s, they were essentially racing each other to measure the speed of light. Foucault's approach used a rapidly rotating mirror instead of a toothed wheel, and it had one crucial advantage that would turn out to change everything. See, Fizeau's toothed wheel was brilliant, but it needed a long baseline. That mirror he bounced his light off of was more than 8 kilometers away, sitting on a hilltop across the outskirts of Paris. That's fine for measuring light in air, but what if you wanted to measure the speed of light in something other than air? What if you wanted to know how fast light travels through water or glass or some other transparent medium? You can't exactly set up an 8-kilometer column of water between two hilltops. It's just not practical. But Foucault's rotating mirror method could work over much shorter distances, and that meant you could fit the entire apparatus inside a laboratory. You could put a tube of water in the path of the light beam and actually measure how fast light traveled through it. And that matters enormously, because there was a huge theoretical question hanging over physics at the time, and the answer depended on exactly this measurement. Here's the backstory. By the mid-1800s, there were two competing theories about the nature of light. One was the particle theory, championed most famously by Isaac Newton. Newton believed light was made up of tiny corpuscles, little particles shooting through space like bullets. The other was the wave theory, which had been argued by Christian Huygens, the same Huygens who calculated the speed of light from Roemer's Jupiter observations. Huygens thought light was a wave, like sound or ripples on a pond. Now, both theories could explain a lot of the same phenomena: reflection, refraction, the basic behavior of lenses and mirrors. But they made one critical prediction that went in opposite directions. The particle theory predicted that light should travel faster in a denser medium, faster in water than in air. The wave theory predicted the opposite, that light should travel slower in water than in air. Think about that. Two theories, both plausible, both explaining most of what people could observe, but making exactly opposite predictions about one specific measurable thing. All you had to do was measure the speed of light in water and compare it to the speed of light in air, and you'd know which theory was right. The problem was that nobody had been able to do that measurement. Until Foucault. So here's how his rotating mirror method worked, and it really is elegant. You start with a beam of light, and you aim it at a mirror that's spinning very, very fast. When the light hits the spinning mirror at just the right moment, it bounces off toward a fixed, curved mirror some distance away. That fixed mirror reflects the light straight back to the spinning mirror. But here's the key. By the time the light makes that round trip, the spinning mirror has rotated just a tiny bit, so the returning light doesn't bounce back along exactly the same path it came from. It comes back at a very slightly different angle. And that tiny angular difference, that minuscule deflection, tells you how long the light took to make the round trip. If you know the rotation speed of the mirror, and you can measure that deflection, you can calculate the travel time of the light, and from that, its speed. The faster the light, the less the mirror rotates during the trip, and the smaller the deflection. The slower the light, the more the mirror rotates, and the bigger the deflection. Now, the deflections we're talking about are incredibly small. We're talking fractions of a degree. But Foucault was meticulous, and he had the mirror spinning at something like 800 revolutions per second. And here's where it gets really good. In 1850, Foucault set up his apparatus with a tube of water in the light path. He ran the experiment, and he found that light traveled slower in water than in air. Slower. The wave theory was right. Newton's particle theory, which had dominated physics for over a century, largely on the strength of Newton's towering reputation, was wrong on this point. Light behaved like a wave, and Fizeau, working independently, actually confirmed the same result around the same time. So despite their rivalry, despite the fact that they were barely speaking to each other, they both arrived at the same conclusion. Light slows down in denser media. It's a beautiful moment in the history of science, because it's one of those cases where the experiment just settles the argument. No more debating, no more philosophical hand-waving. You measure it, and nature tells you the answer. But let's sit with that result for a moment, because it's worth really feeling how strange it is. Light slows down in water. You might think, okay, that makes intuitive sense, right? Water is thicker, denser. It should be harder to move through. Like wading through a swimming pool versus walking on dry land. But that analogy actually supports the wrong theory. If light were made of particles, little bullets, then a denser medium pulling on those particles through some kind of attractive force would actually speed them up, the way gravity speeds up a falling object. Newton's theory predicted that the attractive force of the denser medium would accelerate the light particles. The wave theory, on the other hand, predicted that waves would slow down in a denser medium, similar to how sound waves change speed depending on what they're traveling through. So the intuitive analogy of wading through something thick actually misleads you about the physics. The real explanation is subtler, and it has to do with how electromagnetic waves interact with the atoms in a material, something that wouldn't be fully understood for decades. But we'll come back to that. Now, let's talk about what happened next in the quest to pin down the exact speed of light, because the story takes a wonderful turn involving a man, a mountain, and an octagonal spinning mirror. His name was Albert Abraham Michelson, and he might be the single most important figure in the history of light speed measurement. Michelson was born in 1852 in what is now Poland, but his family emigrated to the United States when he was a child. They ended up in a mining town in Nevada, of all places, during the gold and silver rush. His father was a merchant who sold goods to miners. Young Albert was bright, ambitious, and he wanted to get into the United States Naval Academy at Annapolis. The story goes that he applied and didn't initially get one of the allocated spots. So he traveled to Washington, D.C., and reportedly went directly to the White House to appeal to President Ulysses S. Grant in person. Whether the details of that story are perfectly accurate is debated, but one way or another, Michelson got into the Naval Academy. And it was there that he first became fascinated with the problem of measuring the speed of light. As a young instructor at Annapolis in the mid-1870s, Michelson decided to improve on Foucault's rotating mirror method. He was only about 25 years old. And here's what's remarkable. He did the whole thing on a shoestring budget. His initial experiments cost something like $10 out of his own pocket. $10. He set up his apparatus along the banks of the Severn River near the Naval Academy, using a rotating mirror, a fixed mirror about 500 meters away, and some borrowed lenses, and he got a result of approximately 299,910 kilometers per second. That's astonishingly close to the modern accepted value in 1878 on $10. Michelson would spend much of the rest of his career refining this measurement, obsessively, meticulously, pushing the precision further and further. He became, in a very real sense, the world's foremost expert on measuring the speed of light. In 1907, he became the first American to win the Nobel Prize in Physics, largely for his work on optical precision instruments and the measurements he made with them. But the measurement that would make him most famous, the one that would shake the foundations of physics, wasn't actually a measurement of the speed of light itself. It was a measurement of something that wasn't there. And to understand why that matters, we need to talk about a substance that doesn't exist. By the late 1800s, physicists were fairly confident that light was a wave. Foucault and Fizeau had helped establish that. James Clerk Maxwell had published his extraordinary equations in the 1860s, showing that light was an electromagnetic wave, a self-propagating ripple of electric and magnetic fields moving through space at a specific speed that fell right out of the math. Maxwell's equations predicted the speed of light from first principles, from the fundamental constants of electricity and magnetism. You didn't need to measure it with spinning mirrors. You could calculate it from how strong electric and magnetic forces are. And the number matched. That's one of those moments in physics that just gives you chills when you think about it. The speed of light isn't arbitrary. It's woven into the fabric of electromagnetism itself. But here's the thing that was bothering everyone. If light is a wave, what is it a wave in? Sound waves travel through air. Ocean waves travel through water. Seismic waves travel through rock. Every wave anyone had ever encountered was a disturbance in some medium, some substance that was doing the waving. So what was light waving through? It couldn't be air, because light clearly travels through the vacuum of space. We can see the sun and the stars. So physicists proposed that all of space must be filled with an invisible, intangible substance called the luminiferous ether. Luminiferous, meaning light-bearing. The ether. It was everywhere, permeating everything, perfectly transparent, perfectly weightless, and yet somehow rigid enough to support waves vibrating at incredibly high frequencies. If you think that sounds a little suspicious, a little too convenient, well, you're not alone. But, at the time, it seemed like the only logical option. Waves need a medium. Light is a wave. Therefore, there must be a medium. And this is where Michelson comes back into the story, because he devised what might be the most famous failed experiment in the history of science. The idea was simple in concept, though fiendishly difficult in practice. If the Earth is moving through this ether, like a boat moving through still water, then the speed of light should be slightly different depending on which direction you measure it. If you shine a beam of light in the same direction the Earth is moving through the ether, the light should appear to travel a little slower relative to you, like swimming downstream but measuring the water's speed from the bank. No, actually, think of it this way. Imagine you're on a boat moving through perfectly still water, and you drop a pebble. The ripples spread out in circles from where the pebble hit. But since your boat has moved forward, the ripples ahead of you seem closer together, and the ones behind seem farther apart. If you could measure the speed of those ripples from the boat, they'd seem to move at different speeds depending on which direction you looked. Same idea with light and the ether. If the Earth is plowing through the ether at about 30 kilometers per second as it orbits the Sun, then light traveling parallel to the Earth's motion should have a measurably different speed than light traveling perpendicular to it. So in 1887, Michelson teamed up with a chemist named Edward Morley, and together they built an incredibly sensitive instrument called an interferometer. The Michelson interferometer, as it came to be known, split a single beam of light into two beams traveling at right angles to each other, sent them out to mirrors and back, and then recombined them. If the two beams traveled at even slightly different speeds, the recombined light would show an interference pattern, bright and dark fringes that you could see and measure. The instrument was so sensitive that it could detect speed differences far smaller than what the ether theory predicted. They mounted the whole thing on a massive stone slab floating in a pool of mercury so it could be rotated smoothly without vibration. They ran the experiment over and over, at different times of day, at different times of year, rotating the apparatus to every possible orientation. And they found nothing. No difference. No matter which direction they pointed the beams, the speed of light was the same. The ether wind they were looking for simply wasn't there. The result was so shocking, so contrary to what everyone expected, that Michelson himself considered the experiment a failure. He had set out to measure the Earth's motion through the ether, and instead he had measured zero. No motion, no ether wind, nothing. He was genuinely disappointed. But what Michelson saw as a failure, a young patent clerk in Switzerland would eventually see as the most important clue in all of physics. His name was Albert Einstein, and in 1905, he was 26 years old, working at the Swiss Patent Office in Bern, reviewing other people's inventions for a living. He hadn't been able to land an academic position after finishing his degree. His professors hadn't thought much of him. One of them, a man named Heinrich Weber, reportedly told Einstein he was clever, but refused to listen to anyone, which, honestly, turned out to be kind of the point. Einstein had been thinking about light since he was a teenager. When he was about 16, he posed himself a thought experiment that would gnaw at him for a decade. He asked, "What would it look like if you could ride alongside a beam of light? If you could somehow travel at the speed of light and look over at the light wave next to you, what would you see?" According to the physics of the time, Maxwell's equations, classical mechanics, all of it, you should see a frozen electromagnetic wave, a static, oscillating pattern just hanging there in space, not going anywhere. But here's the thing. Maxwell's equations don't allow for that. There's no solution to Maxwell's equations that describes a stationary electromagnetic wave just sitting still. The equations demand that electromagnetic waves move, and they move at a specific speed, that constant we talked about earlier, the one that falls out of the electric and magnetic constants of free space. Light has to move at light speed. It's not optional. So young Einstein had a contradiction on his hands. Classical mechanics said you should be able to catch up to a light beam if you went fast enough. Maxwell's equations said that's impossible. Light always moves at the same speed. Period. Both couldn't be right. And for years, Einstein turned this over in his mind, poking at it from different angles, while the rest of the physics world was still trying to figure out what went wrong with the Michelson-Morley experiment. Some physicists proposed that the ether existed, but somehow contracted in the direction of motion, which would neatly explain why Michelson and Morley couldn't detect it. The Dutch physicist Hendrik Lorentz and the Irish physicist George Fitzgerald independently came up with mathematical transformations, length contraction, time adjustments, that could save the ether theory by making the null result come out right. And their math was good. Really good, actually. But it was a patch. It was a way of keeping the old framework alive by adding corrections to it, without asking the deeper question of why those corrections were needed. Einstein asked the deeper question, and his answer, when it came, was breathtakingly simple. He said, "What if the speed of light really is the same for everyone? Not because of some trick of the ether, not because of some contraction effect, but as a fundamental law of nature. What if it's not the experiment that's wrong? What if it's our assumptions about space and time that are wrong?" Think about what that means. If you're standing still and you measure the speed of a beam of light, you get about 299,792 kilometers per second. Now, if you're in a spaceship moving at half the speed of light and you measure that same beam, classical physics says you should get a different number. The light should appear slower or faster, depending on whether you're moving toward it or away from it. But Einstein said no. You get the same number, exactly the same, 299,792 kilometers per second. No matter how fast you're moving, no matter what direction, the speed of light in a vacuum is always the same. And if that's true, if the speed of light is truly constant for all observers, then something else has to give, because speed is just distance divided by time. If the speed stays the same, but the motion of the observer changes, then distance and time themselves must be changing. And that's exactly what Einstein proposed in his 1905 paper on the electrodynamics of moving bodies. Space contracts. Time dilates. The faster you move, the more these effects manifest. A clock on a moving spaceship ticks slower than a clock sitting on your desk. A ruler on that spaceship is shorter than an identical ruler in your hand. Not because anything is wrong with the clock or the ruler, but because time and space themselves behave differently depending on your relative motion. This is special relativity. And I know it sounds abstract, maybe even a little unreal, like a thought experiment that doesn't connect to anything you can touch. But here's where it gets practical, and this is one of my favorite examples. You almost certainly interact with special relativity every single day without knowing it. If you've ever used GPS, and you have, your phone uses it constantly, then you've relied on Einstein being right. The GPS satellites orbiting Earth are moving at about 14,000 kilometers per hour relative to you. That's fast enough that their onboard clocks tick slightly slower than clocks on the ground by about 7 microseconds per day due to special relativity. Now, there's also a general relativity effect working in the opposite direction. Because the satellites are farther from Earth's gravitational field, their clocks actually tick faster by about 45 microseconds per day. The net effect is that the satellite clocks gain roughly 38 microseconds per day compared to ground clocks. That sounds tiny. 38 microseconds. But GPS works by measuring the time it takes light speed signals to travel from satellites to your phone. And if you let a 38 microsecond error accumulate without correcting for it, your position would drift by about 10 kilometers per day. Your GPS would be useless by lunchtime. So the system corrects for relativistic effects continuously. Einstein's 1905 insight, that the speed of light is constant and that time is relative, is literally baked into the navigation system that tells you where the nearest coffee shop is. But let's come back to 1905 for a moment, because Einstein wasn't done, not even close. Later that same year, and this is why 1905 is sometimes called his miracle year, his annus mirabilis, he published another paper, a short one, almost like an afterthought, It was only 3 pages long, and in it, he derived the most famous equation in all of science: E equals mc squared. Energy equals mass times the speed of light squared. And here's what's really clever about this. It's not just a formula about nuclear bombs or power plants, although it certainly applies to those. What it's really saying is that mass and energy are the same thing, just expressed differently. And the conversion factor between them, the exchange rate if you like, is the speed of light squared, which is an enormous number. The speed of light is about 300 million meters per second. Square that, and you get 9 followed by 16 zeros. So even a tiny amount of mass corresponds to a staggering amount of energy. This is why nuclear reactions are so powerful. When a uranium atom splits in a fission reaction, the fragments that come out weigh very slightly less than the original atom. We're talking about less than 1% of the mass. But multiply that tiny missing mass by the speed of light squared, and you get the energy that powers nuclear reactors and, unfortunately, nuclear weapons. The speed of light isn't just a speed anymore. It's a fundamental constant woven into the very fabric of how energy and matter relate to each other. And you know what's fascinating? Einstein didn't arrive at E equals mc squared by thinking about atoms or nuclear physics. He got there by thinking about light, by taking seriously the idea that the speed of light is constant and following the math wherever it led. The whole thing cascaded from that one stubborn, beautiful fact that Michelson and Morley had accidentally confirmed 18 years earlier, that light moves at the same speed no matter what. Now, I want to pause here and talk about something that trips a lot of people up, because it tripped up physicists for a long time too. When we say nothing can go faster than the speed of light, what do we actually mean? And why? It's not just an arbitrary speed limit, like a sign on the highway that says 65 miles per hour. It's a structural limit of the universe itself. Here's one way to think about it. As an object with mass accelerates, gets faster and faster, its relativistic mass effectively increases. It takes more and more energy to accelerate it further. As you approach the speed of light, the energy required to accelerate even a tiny bit more approaches infinity. You would need infinite energy to push a massive object to the speed of light. It's not that we lack a powerful enough engine. It's that the mathematics of the universe literally don't allow it. The speed of light is a wall that objects with mass can approach but never reach. But light itself has no mass. Photons, the particles of light, are massless. And because they're massless, they don't just travel at the speed of light. They must travel at the speed of light. They can't go slower, and they can't go faster. They exist only at that speed. From the moment a photon is created to the moment it's absorbed, it moves at exactly 299,792,458 meters per second in a vacuum. And here's something that will really bend your mind if you sit with it. From the photon's own perspective, if a photon could have a perspective, which is a weird thing to say, but bear with me, no time passes at all. Time dilation at the speed of light is total. A photon emitted from a star 8 billion light-years away arrives at your eye, and from the photon's frame of reference, the journey was instantaneous. 0 time elapsed. The entire history of its trip across the universe simply didn't happen from its own point of view. It was emitted and absorbed in the same moment. That's a strange and beautiful idea, and it falls directly out of Einstein's equations. The same equations that started with a teenager wondering what it would look like to ride alongside a beam of light. So by the early 20th century, the speed of light had transformed from a measurement problem, how fast does light go, into something much deeper. It had become a fundamental constant of nature, a cosmic speed limit, a bridge between energy and mass, and the key that unlocked an entirely new understanding of space and time. And the number itself had been refined to extraordinary precision. But there was still work to do, because physicists wanted to nail it down even further. And the methods they developed to do that would lead to one of the most quietly radical decisions in the history of science, a decision that, in 1983, would change the very definition of what a meter is, which sounds like a small bureaucratic thing, but it's actually one of the most profound things that ever happened in metrology, which is the science of measurement itself. Because what happened in 1983 wasn't just a bureaucratic update to some dusty standards document. It was the moment humanity collectively said, you know what? We trust the speed of light more than we trust any physical object on Earth, more than we trust any rod of metal, any wavelength of any atom, any distance we can mark between two scratches on a bar. We trust this number, 299,792,458 meters per second, so completely that we're going to flip the whole thing around and use it to define what a meter actually is. Let me explain why that's such a big deal. For most of history, a meter was defined by a physical thing. In the late 1700s, the French revolutionaries, and this is a fun tangent because you don't usually associate violent political upheaval with precision measurement, but here we are. The French decided they wanted a rational, universal system of measurement. No more feet and thumbs and royal cubits. They wanted something based on nature itself. So they sent two astronomers, Jean-Baptiste Delambre and Pierre Méchain, on a grueling multi-year expedition to measure the arc of the meridian from Dunkirk to Barcelona. The idea was to define the meter as 1/10,000,000th of the distance from the North Pole to the equator, along the meridian passing through Paris. Naturally, it had to go through Paris. The expedition was a nightmare, by the way. It took 7 years instead of the planned one. There was a revolution happening. Méchain was detained in Spain, suspected of being a spy. He also made a measurement error that he discovered but was too ashamed to reveal, and it haunted him for the rest of his life. He eventually died on a later expedition, still trying to correct it. But they finished, more or less, and from their measurements, a platinum bar was cast, 1 meter long. The Maître des Archives, it was called. And that bar, sitting in a vault in Paris, was the meter. That was the definition. If you wanted to know how long a meter was, you compared your measuring stick to that bar, or to a copy of it. Now you can already see the problem, right? A physical bar changes. It expands with heat. It contracts with cold. It wears down over time. It's sitting in one specific place, so if you're in Tokyo or Chicago, and you need to calibrate something, you need a copy of the bar, and copies aren't perfect. By the late 1800s, they'd upgraded to a fancier bar, platinum iridium alloy, kept at a very specific temperature, stored under very specific conditions in a vault at the International Bureau of Weights and Measures in Sèvres, just outside Paris. And that helped. But it was still a bar, still a physical object, still subject to the indignities of being a thing in the real world. So in 1960, they switched to something better. They redefined the meter in terms of the wavelength of light emitted by krypton-86 atoms. Specifically, 1 meter was defined as 1,650,763.73 wavelengths of the orange-red emission line of Krypton 86 in a vacuum. That's wonderfully precise, and it has the advantage of being reproducible anywhere. You don't need a specific bar in a specific vault. Any lab in the world with a Krypton lamp and the right equipment could reproduce the meter independently. That was a huge step forward. But even that wasn't good enough. Because by the 1970s and early 1980s, laser technology had gotten so extraordinarily precise that scientists could measure the speed of light far more accurately than they could measure the Krypton wavelength that defined the meter. Think about what that means. The uncertainty in the speed of light wasn't really about light anymore, it was about the meter. The ruler was fuzzier than the thing being measured. The definition of length itself had become the bottleneck. So in 1983, the General Conference on Weights and Measures made the call. They defined the speed of light as exactly 299,792,458 meters per second. Not approximately. Not our best measurement. Exactly. By definition. And the meter became whatever distance light travels in a vacuum in 1/299,792,458 of a second. The meter was no longer a thing. It was a consequence of light speed and the definition of a second, which itself was already defined by atomic clocks, specifically by the radiation emitted by cesium-133 atoms. And here's what's really clever about this. It means the speed of light can never be measured again. Not in the traditional sense, because it's no longer an empirical quantity. It's a defined constant. If you set up an experiment and get a number that isn't 299,792,458, you haven't discovered that light is faster or slower than we thought. You've discovered that your ruler is wrong. Your measurement of distance is off. The speed of light is the anchor now. Everything else adjusts around it. That might sound circular, but it's actually deeply practical. It means that anywhere in the universe, anyone with a cesium clock and a laser can independently construct a meter to extraordinary precision without needing any physical artifact, without needing to compare anything to a bar in a French vault. The definition is built into the fabric of physics itself, and the precision is stunning. Modern measurements of distance using this framework are accurate to parts in 100 billion or better, so that's where we ended up. The speed of light went from being an unknown, maybe it's infinite, maybe it's finite, who knows, to being the most precisely known constant in all of physics, so precisely known that we stopped measuring it and started defining other things in terms of it. That's a remarkable journey. From Roemer squinting at Jupiter's moons in 1676 to the 1983 redefinition, the whole arc of that story is about humanity slowly realizing that this number isn't just a property of light. It's a property of the universe. But now, let's talk about something that trips people up all the time, because it seems to contradict everything we just said. Light slows down. You've heard this. Light travels slower in water than in air. It travels slower in glass than in water. It travels slower in diamond than in glass. In fact, the whole reason a prism splits white light into a rainbow is that different wavelengths of light slow down by different amounts when they enter the glass. That's dispersion. Newton figured that out in the 1660s with his famous prism experiments, though he was thinking about it in terms of particles, not waves. So what's going on? If the speed of light is this sacred, fundamental, unchangeable constant of nature, if we literally defined the meter around it, how can it slow down in water? Isn't that a contradiction? Here's the thing. It's not. and the resolution is beautiful, but it requires you to think carefully about what's actually happening when light passes through a material. Because the photons themselves, the individual particles of light, are always traveling at c. Always. In the space between atoms, they're moving at 299,792,458 meters per second, full stop. But when light enters a material like glass or water, it's not just sailing through empty space anymore. It's interacting with atoms. Think of it this way. Imagine you're trying to walk across a room, and the room is full of people who keep stopping you to have brief conversations. Your actual walking speed between conversations is the same as always. You haven't gotten slower. But your effective speed across the room, the time it takes you to get from one side to the other, is much slower because you keep getting delayed. That's roughly what happens with light in a medium. A photon enters the glass and gets absorbed by an atom. The atom's electrons get excited. They jump to a higher energy state. Then, after an incredibly brief delay, the atom re-emits a photon. That photon travels at c until it hits the next atom, gets absorbed, re-emitted, hits the next atom, and so on. Each individual absorption and re-emission involves a tiny delay. Add up billions upon billions of these interactions across even a thin piece of glass, and the net effect is that the light takes longer to get through than it would if the glass weren't there. The effective speed, what we call the phase velocity of light in the medium, is slower than c. The ratio of c to this slower speed is what we call the refractive index of the material. Water has a refractive index of about 1.33, meaning light travels about 75% as fast in water as in a vacuum. Glass is around 1.5, so light is about 2/3 as fast. Diamond is about 2.42, which means light in diamond is moving at only about 41% of its vacuum speed. And this is exactly what Foucault confirmed back in 1850, remember? He showed that light really does travel slower in water than in air. That was a key piece of evidence for the wave theory of light at the time, because the particle theory predicted light should go faster in denser media, not slower. Now, there's a deeper quantum mechanical story here about how photons interact with the electromagnetic field inside a material, and the picture I just gave you, photons bouncing from atom to atom, is a simplification. The full story involves the light wave coupling with the oscillating charges in the material to create what physicists call a polariton, which is kind of a hybrid excitation that moves through the medium at less than c. But the essential point holds. The fundamental speed limit hasn't changed. Nothing is actually traveling faster than c. The individual quantum interactions all happen at c. It's the collective, emergent behavior of light passing through matter that produces the apparent slowdown. And this leads to one of the most visually spectacular phenomena in all of physics. Because if light slows down in a medium, that means it's theoretically possible for something else, a particle, say, to travel faster than light in that medium. Not faster than c, faster than the reduced speed of light in that particular material. And when that happens, you get something called Cherenkov radiation. It's named after Pavel Cherenkov, a Soviet physicist who first observed it systematically in 1934, though the theoretical explanation came from his colleagues Igor Tamm and Ilya Frank in 1937. All three of them shared the Nobel Prize in 1958. Cherenkov radiation is essentially the optical equivalent of a sonic boom. When a jet breaks the sound barrier, it's moving faster than the speed of sound in air, and it creates a shock wave. that cone of compressed air that produces the boom. Same idea here. When a charged particle, say an electron, moves through water faster than light moves through water, it creates a cone of electromagnetic radiation. A light boom, if you will. And you can actually see it. It produces this eerie, beautiful blue glow. If you've ever seen photographs of nuclear reactor pools, those fuel rods submerged in deep blue water with this ghostly blue light emanating from them, that's Cherenkov radiation. The charged particles emitted by the nuclear reactions are moving through the water faster than light moves through the water. Not faster than c. Faster than about 225,000 kilometers per second, which is light speed in water. The particles might be doing 250,000 or 260,000 kilometers per second. Still well under the vacuum speed of light, but above the local speed limit in that medium. And Cherenkov radiation isn't just pretty. It's scientifically invaluable. Physicists use it as a detection tool. Some of the most important particle physics experiments and neutrino observatories rely on detecting that telltale blue flash to identify high-energy particles. The Super Kamiokande detector in Japan, for instance, this enormous underground tank filled with 50,000 tons of ultra-pure water, lined with over 11,000 photomultiplier tubes. It detects neutrinos by watching for the faint Cherenkov radiation produced when a neutrino, on extremely rare occasions, interacts with a water molecule and produces a charged particle that moves faster than light in water. That blue glow, that little cone of light, is how they know a neutrino was there. And it was this detector that confirmed, in 1998, that neutrinos have mass, a discovery that won Takaaki Kajita the Nobel Prize in 2015. So even the slowing of light, which seems like a footnote, turns out to connect to some of the deepest questions in physics. But there's another consequence of light's constant speed that we haven't really explored yet, and it's one that affects you personally every single day in ways you probably never think about. It has to do with what happens when light has to carry information, and why the speed of light creates a kind of fundamental delay in everything. Every phone call, every internet search, every financial transaction. Because the speed of light isn't just a physics curiosity, it's an engineering constraint. And in the 21st century, it's a constraint that people are spending billions of dollars trying to work around. The story of how light speed shapes the modern internet is one of those places where pure physics crashes headlong into practical engineering. And it's a story that starts, of all places, at the bottom of the ocean. Think about this. When you tap a search result on your phone, the information you want might be stored on a server in Virginia, or Amsterdam, or Singapore. And the data that comes back to you, the text, the images, the video, most of it doesn't travel through the air. Not for the long-haul part of the journey, anyway. It travels through glass. Specifically, it travels as pulses of light through fiber optic cables, many of which run along the ocean floor, connecting continents. There are over 1 million kilometers of submarine fiber optic cable crisscrossing the world's oceans right now, and the light inside those cables, those laser pulses carrying your data, they're moving fast, incredibly fast. But not as fast as they could be, because they're moving through glass, not vacuum. The refractive index of the glass fiber is about 1.47, which means light in those cables travels at roughly 200,000 kilometers per second instead of 300,000. That's still absurdly fast by any human standard. But here's the thing. When you're sending a signal from New York to London through a cable that's maybe 6,000 kilometers long, even at 200,000 kilometers per second, that signal takes about 30 milliseconds to make the trip. Round trip, you're looking at 60 milliseconds minimum, just from the speed of light alone. Add in the electronic processing at each end, the routing, the switching, and real-world latency on that link ends up being maybe 65 to 75 milliseconds. Now, 65 milliseconds. That's nothing, right? You blink and it's gone. For most of what you do online, browsing, streaming, email, you'd never notice. But there are situations where those milliseconds are worth fortunes, literal fortunes. And this is where the story gets kind of wild, because it takes us into the world of high-frequency trading. In the early 2000s, financial firms realized that if they could shave even a few milliseconds off the time it took to send a trade order from, say, Chicago to New York, they could exploit tiny price differences between exchanges faster than their competitors. We're talking about the Chicago Mercantile Exchange and the New York Stock Exchange, two of the biggest financial markets on Earth, separated by about 1,200 kilometers. Through standard fiber optic routes, the round-trip latency between them was around 14 to 16 milliseconds, and firms were spending hundreds of millions of dollars to cut that number down. One company, Spread Networks, spent about $300 million around 2010 to lay a brand new fiber optic cable between Chicago and New York, following the straightest possible path, blasting through mountains, tunneling under rivers, doing whatever it took to shave distance off the route. They got the round-trip latency down to about 13 milliseconds. And for a while, that was the fastest link, and the firms that leased it had a tiny but enormously profitable edge. But then other companies started looking at the problem differently. They said, wait, the reason fiber is slow isn't just the distance, it's the glass. Light moves slower in glass. So what if we sent the signals through air instead? And that's exactly what happened. Firms started building networks of microwave towers between Chicago and New York, line-of-sight relay chains across the landscape, because microwave signals travel through air at very close to the vacuum speed of light, much faster than light, through fiber. These microwave networks cut the round-trip time down to under 9 milliseconds. Some estimates put the best links at around 8.5 milliseconds. That's getting remarkably close to the theoretical minimum, which would be the straight-line distance divided by c, and you simply can't beat that. The speed of light becomes a hard wall. No amount of money, no clever engineering, can make your signal arrive faster than light allows. Let that sink in for a second. There are companies whose entire business model bumps up against the speed of light as a limiting factor. Einstein's constant, this number that came out of pure physics, thought experiments in 1905, is now the thing that determines who makes money on a stock trade and who doesn't. The universe doesn't care about your trading algorithm. Light goes as fast as light goes. And it's not just finance. The speed of light creates real engineering headaches in computing itself. Inside your computer's processor, electrical signals travel through circuits at a significant fraction of the speed of light, maybe 50 to 70% of c, depending on the medium. A modern processor running at, say, 5 gigahertz completes one clock cycle every 0.2 nanoseconds. In that time, light in a vacuum travels about 6 centimeters. In a wire, maybe 4 centimeters. That means if two parts of a chip need to communicate, and they're more than a few centimeters apart, the signal literally cannot make the round trip in a single clock cycle. This is one of the reasons modern processors are designed the way they are. Compact, with components packed incredibly close together, with elaborate hierarchies of cache memory placed physically near the processing cores. The speed of light dictates the physical layout of the chips in your phone. It's a spatial constraint imposed by a cosmic speed limit. Now, zoom out from chips to something much bigger. Think about space exploration. When NASA's Perseverance rover is operating on Mars, the engineers back on Earth can't drive it in real time, the way you drive a remote control car. Mars, at its closest approach to Earth, is about 55 million kilometers away. At the speed of light, a signal takes over 3 minutes to get there. At its farthest, Mars is about 400 million kilometers away, and the one-way light delay is over 22 minutes. So if you send a command, turn left, you won't know what happened for at least 6 minutes at best, and up to 44 minutes at worst. That's why the rover has to be semi-autonomous. It has to make its own decisions about avoiding rocks and navigating terrain, because the speed of light makes real-time remote control physically impossible. Not technologically impossible, physically impossible. No future technology will ever fix this, because no signal can outrun light. And this gets even more dramatic when you think about missions to the outer solar system. The Voyager 1 spacecraft, launched in 1977, is now over 24 billion kilometers from Earth. A signal from Voyager 1, traveling at the speed of light, takes more than 22 hours to reach us. When mission controllers send a command, they wait nearly 2 full days for the round trip. Every conversation with that spacecraft is a day-long exchange. And Voyager is still in our cosmic backyard. The nearest star system, Alpha Centauri, is about 4.24 light-years away. A signal sent there would take over 4 years to arrive. A round-trip conversation would take 8.5 years. If we ever send a probe to another star, and there are people seriously working on concepts for this, the speed of light means that probe would be on its own, completely autonomous. You couldn't troubleshoot a problem. You couldn't upload a software patch. You couldn't redirect it. Not in any useful time frame. The speed of light turns interstellar space into a kind of isolation chamber. But here's what's really interesting, and this brings us back to something we touched on earlier. The speed of light doesn't just create delays across space, it creates something much stranger. It means that everything you see, everything you observe, is the past. When you look at the moon, you're seeing it as it was 1.3 seconds ago. When you look at the sun, you're seeing it as it was about 8 minutes and 20 seconds ago. If the sun suddenly vanished, just hypothetically disappeared, you wouldn't know for over 8 minutes. You'd still see it shining, still feel its gravity, for those 8 minutes, because the information about its disappearance couldn't reach you faster than light. And when astronomers look at distant galaxies, they're looking back millions or billions of years. The light from the Andromeda galaxy that hits your eye on a clear night left that galaxy about 2.5 million years ago, when our ancestors were just beginning to use stone tools. The Hubble Space Telescope and now the James Webb Space Telescope are essentially time machines. When Webb captures an image of a galaxy 13 billion light-years away, it's seeing that galaxy as it existed 13 billion years ago, less than 1 billion years after the Big Bang. The finite speed of light means the universe comes with a built-in archaeological record. The farther you look, the further back in time you see. And there's a limit, a cosmic horizon, beyond which light hasn't had time to reach us since the universe began. We literally cannot see beyond it. Not because our telescopes aren't good enough, but because the information hasn't arrived yet. It's still on its way, traveling at 299,792,458 meters per second, and it simply hasn't had enough time. This idea that the speed of light defines what you can know, what you can see, what you can influence, it's not just a measurement fact. It's a structural feature of reality, and it connects to something Einstein realized that goes even deeper than special relativity, something that took him another 10 years to work out, something that links the speed of light not just to time and space, but to gravity itself. Because after 1905, Einstein wasn't done. He knew special relativity only handled a specific case, objects moving at constant speeds relative to each other. It said nothing about acceleration, nothing about gravity. And Einstein had a hunch, a deep physical intuition that gravity and acceleration were somehow the same thing. He later called it the happiest thought of his life, this idea that came to him in 1907 while he was still working at the patent office. He imagined a person falling freely, say, falling off a roof, and realized that during the fall, that person wouldn't feel their own weight. They'd feel weightless, as if gravity had switched off. And that simple thought experiment, that moment of imagining what it feels like to fall, set Einstein on a path towards something far more ambitious than special relativity. It would take him 8 grueling years, some of the most intellectually demanding work any human being has ever done, collaborations with mathematicians, wrong turns, public embarrassments, moments of despair. And it would lead him to a theory that reimagines gravity not as a force pulling objects together, but as a curvature in the fabric of space-time itself. And at the heart of that theory, once again, sitting right there in the equations, like a golden thread running through everything, is the speed of light. General relativity, Einstein's masterwork, the theory that describes black holes and gravitational waves and the expansion of the universe, it all comes back to C. And the way it comes back to C is beautiful and strange, because C doesn't just show up as a speed limit anymore. It shows up as a conversion factor, a bridge between the geometry of space and the passage of time. In the field equations of general relativity, the ones Einstein finally published in November 1915, after those 8 years of struggle, C appears raised to the 4th power in the denominator of the main coupling constant. That sounds technical, and it is. But what it means intuitively is this: C is the thing that tells the universe how much a given amount of mass or energy is allowed to bend the fabric of space-time around it. The bigger C is, the stiffer space-time becomes, the harder it is to warp. And because C is enormous, almost 300 million meters per second, C to the 4th power is an astronomically large number, which means space-time is incredibly rigid. You need a colossal amount of mass or energy to produce even a tiny curvature. That's why you and I, sitting here on Earth, don't notice space-time bending around us. The Earth is massive enough to curve space-time just a little, just enough to keep our feet on the ground, but the effect is subtle. You need something like a neutron star or a black hole to really warp the geometry dramatically. And here's what's so elegant about this. In special relativity, C connects space and time. It tells you how to trade one for the other. In general relativity, C connects space and time to matter and energy. It's the same constant doing double duty, linking everything together. The speed of light isn't just about light anymore. It's the structural constant of the universe. It determines how clocks run in a gravitational field, how light bends around massive objects, how the universe itself expands. Every single one of those phenomena has C woven into its description. Let's talk about one of those phenomena, Because it's one of the most mind-bending predictions Einstein ever made, and it took a century to confirm directly. Gravitational waves. When Einstein worked out the math of general relativity, he realized that if you disturb space-time violently enough, say two massive objects spiraling into each other, the disturbance should ripple outward through the fabric of space-time itself, like waves spreading across the surface of a pond when you drop a stone in. And the speed those ripples travel at, the speed of light, exactly c, not approximately c, exactly c. The equations demand it. Gravitational information propagates at the same speed as electromagnetic information, which means if the sun suddenly vanished, just hypothetically blinked out of existence, the Earth wouldn't feel the gravitational change for about 8 minutes and 20 seconds, the same delay as the last photons of sunlight reaching us. Gravity and light are on the same clock, governed by the same speed limit. Now, Einstein himself went back and forth on whether gravitational waves were real physical things or just mathematical artifacts, coordinate tricks that didn't correspond to anything in the actual universe. He even submitted a paper in 1936 arguing they didn't exist, which was rejected by the reviewer, and the reviewer turned out to be right. Einstein had made an error, corrected it, and the corrected paper showed gravitational waves were real after all. But for decades, most physicists treated them as theoretical curiosities. The waves would be unimaginably faint. Even a cataclysmic event like two black holes merging billions of light-years away would produce a distortion in spacetime so tiny that it would change the distance between 2 points a few kilometers apart by less than 1,000th of the diameter of a proton. Measuring that seemed impossible. And yet, on September 14th, 2015, almost exactly a century after Einstein published general relativity, 2 detectors in the United States picked up a signal. The detectors were called LIGO, the Laser Interferometer Gravitational Wave Observatory, and they are among the most sensitive instruments human beings have ever built. One sits in Hanford, Washington. The other is in Livingston, Louisiana, about 3,000 kilometers away. Each one is basically a giant L-shaped tunnel, 4 kilometers long on each arm, with laser beams bouncing back and forth between mirrors at the ends. The principle is Michelson interferometry, the same basic idea that Michelson used in the 1880s to look for the ether, now scaled up to an almost absurd degree of precision. When a gravitational wave passes through, it stretches space along one arm and compresses it along the other by that impossibly tiny amount, and the interference pattern of the laser light shifts just enough to detect. The signal they caught that September morning, it actually arrived at 5:51 a.m. Eastern Time, and the automated systems flagged it within 3 minutes, came from 2 black holes, each roughly 30 times the mass of the Sun, spiraling into each other about 1.3 billion light-years away. The whole event lasted less than a second in the detector, a quick chirp rising in frequency as the black holes whipped around each other faster and faster before merging. And the gravitational waves from that merger traveled across the universe at exactly c, arriving at Earth 1.3 billion years after the event itself. Think about that timeline. When those black holes collided, the most complex life on Earth was single-celled. The waves traveled for over 1 billion years at the speed of light to wash over our little planet, just as we happened to have built an instrument sensitive enough to notice. The detection earned Kip Thorne, Rainer Weiss, and Barry Barish the Nobel Prize in Physics in 2017. And it confirmed something profound about CE. It's not just the speed of electromagnetic waves. It's the speed of gravitational waves, too. It's the speed at which causality itself propagates through the universe. Nothing, no signal, no influence, no information of any kind, travels faster. And that brings us to something people always want to know about. What about faster than light travel? What about warp drives, wormholes, all the science fiction stuff? Here's the honest answer, and it's more interesting than a simple yes or no. Special relativity doesn't say you can't get somewhere quickly. It says you can't accelerate a massive object to or past c. The energy required grows without bound as you approach the speed of light. You'd need infinite energy to reach it, which is why it's a hard limit for anything with mass. But general relativity, the deeper theory, is more permissive in certain weird ways. It describes the geometry of space-time, and there's nothing in the equations that strictly forbids space-time itself from doing unusual things. In 1994, a physicist named Miguel Alcubierre, working at the University of Wales, published a paper showing that general relativity technically allows a solution where a bubble of flat space-time moves through the universe at any speed, including faster than light. The idea is that you wouldn't be moving through space faster than light. You'd be sitting still inside your little bubble while the space behind you expands and the space in front contracts, carrying you along. The ship doesn't violate the local speed limit because locally, inside the bubble, nothing is moving faster than c. It's the fabric itself that's doing the moving. And there's no speed limit on how fast space can expand. We already know that from cosmology, because distant galaxies are receding from us faster than light due to the expansion of the universe, and that's perfectly consistent with relativity. Now, before you get too excited, there are enormous problems with the Alcubierre drive. The original version required exotic matter with negative energy density, stuff that may not exist and that would violate most known energy conditions. The amount of energy involved was initially calculated to be greater than the mass energy of the entire observable universe, which is not a promising engineering spec. Later refinements brought that number down considerably. Some estimates got it to roughly the mass energy of Jupiter, which is still absurd, but at least finite. And there are causality problems. If you can move information faster than light, even by riding a space-time bubble, you potentially create scenarios where effects precede causes, where you could, in principle, send a message to your own past. Most physicists consider that a strong hint that these solutions, while mathematically valid, probably can't be realized in the actual universe. Nature seems to have a deep commitment to protecting causality, and C is the mechanism by which it does so. But here's what's genuinely interesting about all of this, and it's easy to miss if you get caught up in the science fiction angle. The fact that we can even have this conversation, the fact that general relativity permits these exotic geometries as mathematical solutions, tells us something about the richness of the theory Einstein built. The equations are so powerful, so general, that they contain within them descriptions of black holes, gravitational waves, the Big Bang, the expansion of the universe, and yes, even hypothetical warp drives, all from a theory that started with a man imagining what it feels like to fall off a roof, and all of it tied together by C. Let me bring this back to something concrete for a moment, because there's a place where general relativity and the speed of light affect your life in a very direct, practical way, and you've probably used it today. GPS, the Global Positioning System. There are about 31 satellites orbiting Earth at an altitude of roughly 20,000 kilometers, each carrying extremely precise atomic clocks. Your phone figures out where you are by measuring the tiny differences in arrival times of signals from multiple satellites. And since those signals travel at sea, even a tiny error in the clocks translates to a significant error in position. A clock error of just 1 microsecond, 1 millionth of a second, corresponds to a position error of about 300 meters, so the clocks need to be extraordinarily accurate. Here's where it gets interesting. Those satellites are moving at about 14,000 kilometers per hour relative to the ground, which means special relativity predicts their clocks will tick slightly slower than ground clocks, about 7 microseconds per day slower. But they're also 20,000 kilometers above Earth, where gravity is weaker, and general relativity predicts that clocks in weaker gravity tick faster, about 45 microseconds per day faster. The two effects work in opposite directions, and the general relativistic effect wins. So the net result is that the satellite clocks gain about 38 microseconds per day relative to clocks on the ground. If you didn't correct for this, GPS positions would drift by roughly 10 kilometers per day. The system would be useless within hours. So every GPS satellite has its clock rate adjusted before launch to compensate for both relativistic effects. Every time you open a map on your phone, you're relying on corrections that come directly from Einstein's theories, both special and general, both rooted in the speed of light. And that's the thing about C that I find most remarkable when you step back and look at the whole picture. It's not just a number. It's not just a speed. It's the thread that connects an astonishing range of phenomena, from the color of stars to the accuracy of your navigation app, from the reason nothing can escape a black hole to the reason your microwave heats food. It connects Maxwell's equations to Einstein's field equations to the quantum theory of light. It connects Rømer, staring at Jupiter's moons in 1676, to engineers calibrating satellite clocks in 2024. And the deeper physicists dig, the more central it becomes, because C isn't just about electromagnetism or gravity. It shows up in places that seem to have nothing to do with light at all. It appears in the equations governing the strong nuclear force, the weak nuclear force, the behavior of every fundamental particle. It's baked into the structure of quantum field theory at the most basic level. Because every quantum field theory that describes our universe is what physicists call Lorentz invariant, meaning it respects the symmetry that special relativity established, the symmetry that C makes possible. And that symmetry, that Lorentz invariance, is one of the most quietly powerful ideas in all of physics. It's worth sitting with for a moment because it touches everything. So what does it actually mean for a theory to be Lorentz invariant? It means the laws of physics look the same no matter how fast you're moving, as long as you're moving at a constant velocity. The equations don't change shape. The predictions don't shift. And the speed that anchors that whole symmetry, the speed that appears over and over in the mathematical machinery that keeps everything consistent, is C. Not because light is special in some mystical way, but because C is the speed at which causality itself propagates. It's the fastest rate at which any influence, any signal, any change in a field can ripple from one point in space-time to another. Light just happens to travel at that speed because photons are massless, and anything massless is forced to move at exactly C. But if photons didn't exist, if light had never been discovered, that speed would still be there, built into the fabric of reality. Physicists would have found it eventually through other means. And here's where it gets really interesting, because when you look at quantum field theory, the framework that describes all the fundamental particles and forces, C is everywhere. Not as a guest appearance, not as a cameo. It's structural. Take quantum electrodynamics, QED, which describes how electrically charged particles interact through the exchange of photons. That theory was developed in the late 1940s, primarily by Richard Feynman, Julian Schwinger, and Shinichiro Tominaga, all three of whom shared the Nobel Prize in 1965. QED is often called the most precisely tested theory in all of science, and that's not an exaggeration. Its predictions match experimental measurements to something like 10 decimal places. 10. That's like predicting the distance from New York to Los Angeles, and being accurate to less than the width of a human hair. And at the heart of QED, woven into every propagator, every vertex, every Feynman diagram, is C. It determines how virtual photons mediate the electromagnetic force, how quickly the influence of a charge can be felt by another charge, how the field responds to changes. Without C baked in, the whole thing falls apart. But it's not just electromagnetism, the weak nuclear force, the one responsible for certain types of radioactive decay, the one that powers the proton-proton chain inside the sun. That force is described by a quantum field theory too, and that theory is also Lorentz invariant. The W and Z bosons, the particles that carry the weak force, are massive, so they don't travel at c. They're sluggish compared to photons. But the equations governing their behavior still have c embedded in them, because the underlying space-time symmetry demands it. The same is true for quantum chromodynamics, QCD, the theory of the strong nuclear force that binds quarks together inside protons and neutrons. Gluons, the carriers of the strong force, are massless like photons, so they do travel at c. But even if they didn't, the theory would still need C in its structure, because without Lorentz invariance, the predictions would depend on how fast the observer is moving, and that would mean the laws of physics aren't universal. The whole edifice of modern particle physics rests on this. Now, you might be thinking, okay, C shows up in all these equations, but is it really the same C? The speed of light in a vacuum? And the answer is yes, it's exactly the same constant. 299,792,458 meters per second. The same number Michelson was chasing with his interferometers, the same number Maxwell derived from the permittivity and permeability of free space, the same number that defines the meter. It's all one thing. And this is part of what makes physics so strangely beautiful, that a single constant can play so many roles simultaneously. It's the speed of light, yes, but it's also the speed of gravity, the speed of gluons, the conversion factor between mass and energy, the ratio that determines how space-time curves, and the fundamental speed limit of causality. All the same number. And this unity isn't something physicists just assert. It's been tested. In 2017, when the LIGO and Virgo observatories detected gravitational waves from two merging neutron stars, an event called GW170817, something remarkable happened. About 1.7 seconds after the gravitational wave signal arrived, the Fermi Gamma Ray Space Telescope detected a burst of gamma rays from the same event. The source was about 130 million light-years away. So the gravitational waves and the light waves had been traveling for roughly 130 million years, side by side across the cosmos, and they arrived within less than 2 seconds of each other. When you do the math, that constrains the difference between the speed of gravity and the speed of light to be less than about 1 part in a million trillion. They're the same speed. To an almost absurd degree of precision, gravitational waves and electromagnetic waves travel at exactly c. That single observation killed off a whole family of alternative theories of gravity that had predicted slightly different speeds. Years of theoretical work, gone in 1.7 seconds. That's the power of a clean measurement. And this brings us to something that I think is one of the deepest questions you can ask about C, a question that physicists are still genuinely wrestling with. Why this value? Why 299,792,458 meters per second and not some other number? Is there a reason? Or is it just arbitrary? Now, part of the answer is that the numerical value depends on your units. We chose meters and seconds based on human scale conventions. The meter was originally defined as 1/10,000,000th of the distance from the equator to the North Pole, and the second was defined based on the rotation of the Earth. These are accidents of human history. If we used different units, c would be a different number. In fact, in many branches of theoretical physics, people work in what are called natural units, where c is just set equal to 1. Not 1 meter per second, not 1 anything, just 1. No units. In that system, speeds are expressed as fractions of c, and the equations become much cleaner. Space and time have the same units. Mass and energy have the same units. It's elegant, and it reveals something important. The numerical value of c isn't deep. What's deep is its existence. The fact that there is a finite invariant speed connecting space and time. That's the physical content. The number is just a consequence of our measurement conventions. But even granting that, there's a deeper version of the question. In physics, c is related to other fundamental constants. It shows up in the fine structure constant, alpha, which is roughly 1/137 and governs the strength of the electromagnetic interaction. Alpha is a dimensionless number. It doesn't depend on your choice of units. And it's built from c, Planck's constant, and the elementary charge. If c were different but the other constants stayed the same, alpha would change, and that would change the strength of electromagnetism, which would change the size of atoms, the energy levels of electrons, the rates of chemical reactions, the stability of molecules. Life as we know it depends on alpha being very close to the value it has. Change it by even a few percent, and stars burn differently, chemistry works differently, complex structures might not form at all. This is the kind of thing that keeps theoretical physicists up at night. Is there some deeper principle that fixes these constants? Some underlying theory from which c and Planck's constant and the charge of the electron all emerge as necessary consequences? String theory has tried to answer this. Loop quantum gravity has tried. So far, no one has succeeded. The constants remain, as far as we can tell, free parameters, numbers that have to be measured, not derived. They're inputs to our theories, not outputs. Some physicists find this troubling. Others find it liberating, or at least humbling. It suggests that our universe might be one of many possible universes, each with different values of these constants, and we happen to live in one where the values permit complexity, chemistry, stars, planets, and eventually, someone lying in bed listening to a story about the speed of light. This is the anthropic argument, and it's controversial because it feels more like philosophy than physics. It doesn't make predictions. It doesn't tell you what to go measure next. But it's hard to dismiss entirely because the fine-tuning is real. The constants really do seem to be balanced on a knife's edge. And c sits right at the center of that balance. Not because it's the most important constant. You could argue Planck's constant, or the gravitational constant, deserve equal billing. But because it's the one that connects the most domains. It links electromagnetism to space-time geometry, to quantum mechanics, to nuclear physics. It's the universal translator, the conversion factor, that lets you move between different descriptions of reality. There's a beautiful way to think about this that I want to leave you with, at least for now. Imagine you're an engineer, and someone hands you the blueprints for the universe. You open them up, And you see all these different systems: gravity, electromagnetism, the nuclear forces, quantum mechanics. And at first, they look separate, like different departments in a company that don't talk to each other. But then you notice that the same constant keeps appearing in all of them. The same number, linking space to time, energy to mass, frequency to wavelength, force to curvature. And you start to realize that these aren't separate systems at all. They're different views of the same underlying structure. And the constant that keeps showing up, the thread running through all of it, is C. Which raises maybe the most tantalizing question of all. A question that takes us right to the bleeding edge of what physics understands and what it doesn't. If C is so fundamental, if it's woven into the fabric of space-time itself, then what happens at the scales where space-time might not be a fabric at all? Where the very idea of distance and duration loses meaning, and the stage on which everything plays out might dissolve into something stranger than we have words for? That's the question that keeps theoretical physicists up at night, which is a little ironic, given that you're trying to fall asleep. But stay with me here, because this is where the story of C reaches its most mysterious frontier, and honestly, it's also where it becomes the most beautiful. So let's think about what it means for space-time to break down. Throughout this whole journey, we've treated space-time as a smooth, continuous thing. Einstein's general relativity describes it as a fabric that can bend and stretch and ripple, but it's still fundamentally smooth. You can always zoom in further. You can always imagine a smaller patch of space, a shorter interval of time. There's no grain to it, no pixelation. It's like a perfectly smooth sheet that goes on forever in every direction and at every scale. But here's the thing. We know that can't be the whole story. And the reason we know is that general relativity and quantum mechanics, the two greatest theories in physics, refuse to play nice with each other at very small scales. General relativity says space-time is smooth. Quantum mechanics says everything is fuzzy and uncertain at small enough scales. Put them together, and you get nonsense. The math breaks. You get infinities that can't be tamed, predictions that make no physical sense. And the scale where this breakdown happens has a name. It's called the Planck scale. The Planck length is about 1.6 times 10 to the negative 35 meters. That's so small, it makes a proton look like a galaxy. To give you a sense of it, if you took an atom and blew it up to the size of the observable universe, the Planck length would still be smaller than a grain of sand. It's absurdly, incomprehensibly tiny. And the Planck time is the time it takes light to cross one Planck length, which works out to about 5.4 times 10 to the negative 44 seconds. These aren't just arbitrary numbers. They're built from the fundamental constants themselves, C, the gravitational constant G, and Planck's constant h bar. Max Planck first identified these natural units way back in 1899, before Einstein, before quantum mechanics, before anyone really understood what they meant. He just noticed that you could combine these three constants in a way that gave you a natural unit of length, time, and mass, and he wrote them down almost as a curiosity. But now, more than a century later, most physicists believe the Planck scale is where something genuinely new happens. Not just a mathematical curiosity, but a physical threshold. Below that scale, our usual notions of space and time probably don't apply. The smooth fabric of space-time might give way to something else: quantum foam, spin networks, vibrating strings, causal sets, depending on which approach to quantum gravity you favor. And here's where C enters the picture in a really profound way. If space-time itself is emergent, if it's not fundamental but arises from something deeper, then c might be emergent too. The speed of light might not be a bedrock feature of reality. It might be a property that emerges when you zoom out far enough from the Planck scale, the way temperature emerges from the collective motion of molecules, even though no individual molecule has a temperature. Think about that for a second. We've spent this whole time talking about c as this deep, fundamental constant woven into the structure of everything. And it is, at every scale we can probe. But it's possible, just possible, that at the very bottom of reality, there is no speed of light. There's no space for it to cross, no time for it to take. There's just whatever the deeper structure is. And c crystallizes out of that structure, the way ice crystallizes out of cooling water. Now, I want to be really honest with you here. Nobody knows if this is true. This is the frontier. This is where established physics ends and speculation begins. But it's informed speculation, grounded in real theoretical frameworks that serious people have spent decades developing. One of those frameworks is loop quantum gravity, which was pioneered in the late 1980s and 1990s by Abhay Ashtekar, Carlo Rovelli, and Lee Smolin, among others. In loop quantum gravity, space isn't continuous. It's made of discrete chunks, tiny, indivisible units of volume linked together in a network. The geometry of space emerges from the way these chunks connect, the way a piece of chainmail emerges from individual interlocking rings. In this picture, the Planck length isn't just the scale where things get weird. It's the actual minimum size of a spatial unit. You literally can't have a distance shorter than the Planck length, because there's nothing smaller to measure. And if that's true, then c, the relationship between space and time, would be a large-scale average, a macroscopic property that emerges from the collective behavior of these discrete units, the way the speed of sound in air emerges from the average behavior of billions of colliding molecules. String theory takes a different approach, but arrives at a similarly humbling conclusion. In string theory, the fundamental objects aren't point particles, but tiny vibrating strings, and they live in a space that might have 10 or 11 dimensions, most of which are curled up so small we can't see them. The properties of particles, their masses, their charges, their interactions, are determined by how these strings vibrate, the way different notes emerge from a guitar string depending on how it's plucked. In this framework, the constants of nature, including c, might be determined by the shape and size of those extra dimensions. Change the geometry of the hidden dimensions, and you change the constants. Which means c isn't a universal truth. It's a local fact, specific to the particular configuration of extra dimensions that our universe happens to have. Other configurations, other universes in the hypothetical multiverse, might have different values, or the concept might not even translate. And then there's an even more radical idea, one that's gained traction in recent years, especially through the work of physicists like Nima Arkani Hamed and others exploring what are called amplituhedra and related geometric structures. The idea is that space-time itself might not be fundamental at all, not just that it's grainy at the Planck scale, but that it's entirely derived, a kind of holographic projection from a deeper mathematical structure that doesn't involve space or time in any recognizable way. In this picture, asking, "What is the speed of light?" is a bit like asking, "What is the frame rate of a movie?" The answer tells you something about the projection, about the format of the display, but nothing about the deeper story being told. The speed of light would be a feature of the representation, not of the underlying reality. Now, I realize this might sound like we've drifted pretty far from Romer timing the eclipses of Io, or Fizeau spinning his toothed wheel on a hilltop outside Paris. And we have. But that's the arc of this story. It starts with practical measurement, someone with a telescope and a clock, trying to figure out whether light takes time to travel. And it ends with the deepest questions humans have ever asked about the nature of reality. And the thread connecting all of it is this one constant, this one number, this speed that turned out not to be just a speed. Here's what I find most moving about the whole story, if you want to know the truth. Every generation of physicists thought they were close to the bottom. Newton thought he'd found the fundamental laws. Maxwell thought his equations were the final word on light. Even Einstein, after general relativity, spent decades searching for a unified field theory, convinced the answer was just around the corner. And each time, the answer turned out to be deeper than anyone expected. The speed of light went from a measurement problem to a property of electromagnetism, to a feature of space-time geometry, to a structural constant of quantum field theory, to, maybe, an emergent property of whatever lies beneath space-time itself. Each layer revealed more, and each layer raised new questions. And right now, in this moment in history, we're in one of those between times. We have extraordinary theories that work with extraordinary precision. Quantum electrodynamics matching experiment to 10 decimal places. General relativity predicting gravitational waves detected after 100 years. The Standard Model cataloging every known particle and force. But we also know these theories are incomplete. They don't fit together. Dark matter and dark energy make up 95% of the universe, and we don't know what they are. The hierarchy problem, why gravity is so much weaker than the other forces, remains unsolved. And the nature of the Planck scale remains hidden behind an energy barrier we may never be able to cross experimentally. But here's the kicker. People are trying. They're building more sensitive gravitational wave detectors, like the planned LISA mission that will put laser interferometers in space, with arms millions of kilometers long instead of LIGO's 4 kilometers. They're studying the cosmic microwave background for subtle signatures that might reveal quantum gravitational effects from the first fraction of a second after the Big Bang. They're colliding particles at higher and higher energies, searching for deviations from the Standard Model that might point toward new physics. And they're doing pure mathematics, exploring the abstract structures that might underlie space-time, looking for the deeper language in which the laws of physics are really written. And through all of it, C remains the guide. It's the conversion factor, the bridge, the Rosetta Stone. Whatever the next theory turns out to be, whatever replaces or extends general relativity and quantum mechanics, it will have to reproduce C in the appropriate limit. It will have to explain why, at the scales we can observe, there exists a finite, invariant speed that links space to time and energy to mass. Any theory that can't do that is wrong, no matter how beautiful its mathematics. So what do you take away from all this? Maybe just this. The speed of light is one of those rare things in science that gets more interesting the more you learn about it. It starts as a simple number, 299,792,458 meters per second, and it becomes a window into the deepest structure of the universe. It connects the everyday to the extraordinary. The fiber optic cable carrying your internet signal, the GPS satellite correcting for time dilation overhead, the starlight that traveled for billions of years before landing on the mirror of a telescope. They're all governed by the same constant, the same fundamental relationship between space and time. And maybe the most comforting thing about it, especially right now, as you're lying there, and the world is quiet is that it's constant. In a universe full of change and uncertainty, where stars are born and die and galaxies drift apart and everything is in motion, C doesn't change. It's the same here as it is in the most distant galaxy. It's the same now as it was 13.8 billion years ago. It's the one fixed point in a universe that has no center, no edge, no preferred frame of reference. Wherever you are, however you're moving, the speed of light is the same. It's the one thing everyone in the universe can agree on. And that's a strange and wonderful thing to know, that the universe, for all its complexity, has this deep simplicity at its core, this one constant that ties everything together, that someone like Roemer could glimpse it in the 17th century by watching a moon disappear behind a distant planet, and that 350 years later, we're still uncovering what it means. So let that thought settle. Let it be the last thing turning over in your mind as you drift off. The speed of light, not just a number, not just a speed, but a thread running through the entire fabric of reality. From the first moment of the universe to this quiet moment right now. From the largest structures in the cosmos to the smallest scales we can imagine. Always there, always the same, a constant in every sense of the word. And that's enough for tonight. That's more than enough. Let it go. Let your thoughts soften and rest